So this video is going to show you how to do hierarchical multiple regression analysis. So if you've already seen the data set that was used in the multiple regression, you'll be familiar with this data set in which we've got BMI, which as previously described on the multiple regression video was log transform to make sure it had a normal distribution. Higher scores mean greater BMI. Anxious attachment scores on anxious attachment scale. Higher scores mean greater anxious attachments. And parent skill score. Higher values mean greater perceived skill of your parents when you were growing up, particularly in regard to feeding practices. In addition, and what we didn't look at last time, was age and gender in this data set. So we've also got each of the participants' age and the gender as well. And what we're interested in this data set was the extent to which anxious attachments and parent skill score predicted BMI. So in our previous video we just looked at these two predictors predicting BMI in a multiple regression. However, what could happen is, and what is very commonly done, well, someone may want us to control for age and gender of the participants. Age and gender may be associated with BMI in this population, so what we can do is we can add these two factors to the regression. Now of course we could just do a normal multiple regression in which we just put these four predictors into our regression and saw how they predicted BMI. However, the experimental hypothesis is particularly focusing on anxious attachments and parent skill score. We're not that interested in these two variables. If anything, they're a bit of a nuisance. They are things that are likely to influence BMI in some way, but not part of our hypothesis. They're not something we're particularly interested in. So what we can do is we can set up our regression analysis in a way that lets us look and control for the impact of these two things while still exploring the effect of these two items. And what we're going to be looking at is what's called a hierarchical regression to do this. So all the principles that we discussed in the previous video with multiple regression are the same. We've got a few new statistics, but they're just variations on what we've looked at before. So one thing we should just quickly draw your attention to is the fact that you do have a categorical predictor here. Okay, it's a nominal predictor, it means categorical, and we've got gender, and we've coded it as female and male. This is fine to use. We can have a categorical predictor, but only if it has two levels. We can't have categorical predictors that have three or more levels. And at the end of this video, I'll put in a brief explanation of why this is the case, and also a really simple way that you can interpret regression coefficients which have binary categorical predictors such as gender in this example. So what we're going to do in this analysis is we're going to look at the impact of anxious attachments and parent skill score on BMI after controlling for the age and gender of our participants. So essentially we're going to look at how much variance in BMI these two variables explain after controlling for the variance already explained by age and gender. The analysis will also give us regression coefficients for each of our four predictor variables. So to do a hierarchical regression, it's almost exactly the same process, but with an additional step to it. So we just go to Analyze, Regression, and Linear as before. So this is our previous analysis that we did, in which we've got BMI as our dependent variable, and we've got anxious attachments and parent skill score. However, now what we want to do is we want to control for age and gender before we look at these factors. So we can remove those. What we do is we put in age and gender here. And as you see, it says block 1 of 1. In the previous example we used only had one block, but now we want to look at more blocks. So what we're going to do is say age and gender is our block 1, then we click next, and we add anxious attachment scores and parental skill score into block 2. We could keep adding blocks and so on, depends on obviously the power, how many participants you've got, the number of variables you're interested in, and so on, as to what you actually add to these things. So we always, as I said in the previous video, which we looked at just normal multiple regression, we always look at the enter method. We don't look at these different ones. I never recommend looking at those at all. So we've told our regression analysis actually got two blocks. We've got our demographics that we control for, then our two variables of interest. We do want to ask for some additional things. We need to ask for this. This is an R squared change This statistic essentially is going to tell us how much the R² statistic changes between block 1 and block 2. We can keep our collinearity diagnostics because this will tell us whether we've got problems with multicollinearity, and we can also ask for this, the Durbin-Watson statistic, which I will explain when we come to that as well. Click continue there. Now again, there's loads of different options, but we're just going to leave it as that, and we're going to analyse this as we've just set it up there. So we just click OK, and this gives us our output for our hierarchical regression. As previously, not that much has changed. You can see we've got a descriptive statistics table, which has got BMI, age, gender, anxious attachment score, and parent skill score. Actually, every variable that's in our regression model. Correlations appear as well. So this is showing the correlations between all our variables. So the correlation between BMI age, BMI gender, BMI anxious attachments, BMI parent skill score, and so on. It does everything twice. So you can see we've got the correlation between BMI and age there, and we've got the correlation between age and BMI there. Everything's doubled up, so we only need to look at half of this. We could use that if we wanted to report our descriptive statistics along with the correlation matrix as well, and so it gives us some relatively useful information. But particularly the descriptive statistics table, you probably want to give a table of descriptives when you're writing it up. So now if you look at our next box here, this is just the variables entered and removed. Now you can see it's changed a little bit from the previous example. We've got two models, model 1 and model 2. So these are our blocks essentially. So we've got block 1, model 1 is gender and age, and we use the enter method to put those into our regression equation. And we've got 2, model 2, parent skill score and anxious attachment score, and we use the enter method. Our BMI, our dependent variable, is still BMI, of course. So we know we've set our regression correctly. Now this table is now got a lot of additional statistics. So previously the model summary table just had R squared, adjusted R squared, and standard error of the estimate. What this has produced is something slightly different now. You can see we've got change statistics, and these refer to variance that is accounted for by model 2, by parent skill score and anxious attachment combined, after controlling for the variance that's been explained by model 1, step 1, gender and age. So if we just go through this table, we can ignore R, we don't really report that statistics, not that useful. Let's look at our R squared statistic. You can see, if we interpret the R squared statistic here, you can see that, okay, step 1 predicted about 11% of variance, and then model 1 plus model 2, so the two things combined predict about 33% variance. If you look at the more conservative adjusted R squared, you can see that's a little bit smaller in both cases. So overall, our 4 variables predict 33% of variance in BMI. This is what this refers to. This is a cumulative amount of variance. So what's new though is this aspect of it, and what this basically tells us is that step 1, as you can tell from this bit as well actually, that step 1 predicts 11% of variance. Now what's critical is this value here. This is the amount of variance that block 2 or model 2, parent skill score and anxious attachment score, predict after we control for this approximate 11% of variance. So this is additional variance. This variance associated with the first model is now accounted for, so it cannot be explained by anything else because we know age and gender explain it. So this is additional variance. So we know our 2 variables that we're really interested in, that predicts an additional 22% of variance approximately. In addition, it gives us these very useful statistics here as well. This F change is an F statistic from an ANOVA, and we've got DF, the 2 degrees of freedom, DF1, DF2, and the sig of F change, and this is just p-values. So taken together, we just look across this row here, this tells us that step 1 predicts approximately 11% of variance. The F change statistic is 4.23. There's your degrees of freedom, and this is statistically significant. So this tells us that step 1, age and gender, predicts approximately 11% of variance in BMI, and this is a statistically significant amount of variance explained. Now, this level here, what this is telling us is step 2 accounts for an additional 22% of variance in BMI after controlling for age and gender, and there's the F statistic, it's degrees of freedom, and this is statistically significant. So even after we control for the variance that we can account for by age and gender, our two variables of real interest, parent skill score and anxious attachment score, predict a significant amount of variance in BMI. So this is basically telling us at each step whether these variables predict a significant amount of variance after controlling for everything that's been put in previously in the regression equation. Now, you'd think that would make this table completely redundant, but it doesn't, because these are the model fit statistics for each step of the regression equation. But we also should, it's good practice to say, okay, is the overall regression model significant? This will so rather than just looking at the broken down model, just overall are your 4 predictors significant? So to do that, we need to look at our overall R² statistic here, and this tells us, this value here says overall the 4 variables together predict about 33% of variance, and we look at this line in the ANOVA table here, because this is the overall model, this is cumulative, and we say this 33% of variance is statistically significant as well, and we've got our F statistic, we've got our degrees of freedom as well. So the first step really, we'd write up overall the regression model was statistically significant, and you just write that for the overall regression model. Now, when we write these things up, it's often a really neat way to write up these regressions is to tabulate things. The first part of the write-up then, when we're doing this, is to look at this sort of stepwise increase in variance, and we'd write this up in a table. So this is the table here, and what this table is essentially showing is that the first 2 variables have an R² change of 0.11, it's got an F value of 4.23, its degrees of freedom of 269, and this is statistically significant, and that accounts for those 2 variables. Now the next bit of the table is telling us that after controlling for these 2 variables that we include in step 1, we predict another 22% of variance with our R² change of 0.22. The F value for this is 10.68, degrees of freedom at 267, and this is highly statistically significant as well. So this basically tells us each step is a significant predictor, and it's broken down the amount of variance that are accounted for by age and gender, and then the amount of variance accounted for by parent skill score and anxious attachment score after controlling for the first 2 variables. So that's all very well. So when we're looking at what are the individual predictors in our regression model, we look at the coefficients table, and you can see now we've got model 1 and model 2. In this table, model 1 is just the 2 variables that we put into the first block of our regression, and then model 2 is all the variables we put in together. And this is the section that you want to be looking at. You only look at what we call the simultaneous model when we're looking at the individual regression coefficients. If you have a look closely, you'll see, say for example, we look at the effect of age here, and we see its p-value is 0.342. In model 1, its p-value is 0.762, so it changes. This is because the regression coefficients that appear here in the simultaneous model all take into account the presence of each other. So the presence of these 2 variables influences the predictive utility of this variable, and that's why we see a change Sometimes it gets more significant, less significant, doesn't really matter. We only should really be looking at what we call our simultaneous model here when all variables are considered together. So if we look at this, it's relatively easy to interpret. It's just like any other regression analysis if we didn't have any steps in it at all, any blocks in it. So we could look at age, and as you can see here, age is not a significant predictor of our participants' BMI. Gender is a significant predictor of BMI, and as you can see, it's a positive association. So that's a bit confusing. How can you have a positive association, as in like a positive correlation almost, between gender, which is in this data set male, female, and BMI? Well, the way we can think about this is if we go back and just quickly look at our raw data. So when we go back to this and we see females are coded as 0 and males are coded as 1. So males are the higher category, female 0, male 1. So what this essentially means then in this context is, because it's a positive number, this means that those in the higher category, the category we coded as 1, have a greater BMI than those in the lower category, the one we coded as 0. So what this basically tells us is that within this data set that males have a higher BMI than the female participants. If we'd coded it the other way around, this would just be the same value, but it would be a negative. So if you coded males as 0 and females as 1, that would become negative. So that's how you interpret that. I'll show you a bit more of an extended example of that later. So just to move on to the others, as you can see, anxious attachment score, as we've seen previously, has a positive association with BMI. Parent skill score has no significant correlation with BMI. So we've got two significant predictors, which are gender and anxious attachments, and age and parent skill score does not predict it. And we'd write this up in the same table, in which we'd simply show the statistics from the simultaneous model, and therefore the reader has got a nice clear breakdown of what are the significant predictors and the direction of that relationship in this table. There's a few other things that we could look at as well. So one important factor we probably want to look at is our variance inflation factor. Again, only looking at the simultaneous model. All the figures are very near 1, which is indicative of having no multicollinearity at all. And as I said previously, you should only really start being worried about this as an issue if this value is 3 or more. So we don't see there's a problem here. The other thing we can briefly check as well is our Durbin-Watson test. So this is the test of serial auto-kill linearity, and we know this should be near 2. Scores can range between 0 and 4. And basically, if figures are less than 1, it's problematic. If figures are greater than 3, it's problematic. And as we can see in this example, we don't have a problem. So overall, our write-up, when we look at this, we have an overall significant model. Our 4 predictors predict a significant amount of variance within our dependent variable. We also know that age and gender predict a significant amount of variance, but only gender is a significant predictor out of those 2 variables. We know that after controlling for age and gender, anxious attachments and parent skill score predict a significant amount of variance in BMI, but we know that only anxious attachment out of the 2 variables is a significant predictor of BMI, and that's a positive relationship in as much as anxious attachment increases, so does participants' BMI. So this part of the video is going to give you an explanation of how to understand categorical predictors in multiple regression, and also why you can't have more than 2 categories in your predictors. So from this graph here, this is just a simple slope done for, we've got our dependent variable here is BMI that we had in our regression, And then we asked participants to fill in the sex, whether they were female, which we coded as 0, or male, which we coded as 1. So what a regression is essentially doing, as you'll know from lectures, is it's just trying to plot a slope for a relationship between two variables. If you've got two categories in your predictor, you can plot a slope, and the slope makes statistical sense because you've got your female scores and the male scores, and then the line between them represents a slope. So in this case, the slope is a beta of 0.49. So it's a positive slope, and the beta is 0.49. Now, if we categorize things in a different way, so if instead of having females category 0 and males as 1, we flipped it, so males are 0 and females are 1, what would happen here is simply the direction of the slope would change. The mathematical value of this slope, the beta, would remain constant. It doesn't matter which way you code it, the beta value remains the same. The only thing that changes is the direction of the association. So now it becomes a negative association between participant sex and the BMI. So all you need to do to interpret these predictors is simply, if the highest scores in the lower category, as it is in this case, this was going to give you a negative slope. If the highest score is in the category categorized as higher, like in this example, this gives you a positive slope. You can even do this just looking at the mean difference between these two groups. So if we looked at the mean BMI for males, the mean BMI for females, we'd know if we're going to have a positive or negative association. So we can do this with dichotomous variables, so we've only got two levels of the variable. However, you cannot use multi-categorical variables. So this is an example that's actually taken from an ANOVA example we did last term, in which we had IQ of our participants, and we've got our Coldplay fans, our G.G. Allen fans, and our Neil Young fans. And you couldn't use this as a predictor in your regression analysis. And the reason for this is the regression coefficient will change according to the order you do these things. In the previous example, the regression coefficient was 0.49, whether you coded males as 0 or males as 1. It didn't matter, just the direction changed. However, for this, if you try to run a regression slope, it would actually change according to the order you put these things in. So let's say, for example, we put them in this order, so Coldplay fans for the lowest IQ, then G.G. Allen fans, and then Neil Young fans. And this is the relationship between these variables. And what the regression would do, it'll try and fit a slope. It'll try and fit a line of best fit. It's going to treat these variables, these three variables, as though they're continuous. It won't view them as a category at all, and it'll just try and put a slope between them. And let's say it gives a positive slope in this example of 0.42. So, well, if we were to change these things, for example, we put Neil Young as 0, Coldplay as 1, G.D. Allen as 2, we see a change in all these variables, and actually the slope would look completely different, and in fact it'd be a negative slope in this example. Even though none of the absolute values associated with each of these groups changed, the regression slope would be very, very different. So we see positive slope when it's in that order, and then in this order it'd be a negative slope. So because there's no order in which you can put these variables in that makes a logical sense, then you cannot run a regression with these variables as a predictor, because if you change the order, it will completely change the regression slopes, because all the regression analysis is going to do is treat these as continuous variables. It can only work if you have a dichotomous variable with two categories only.